So good day everyone, I'm Joshua V. Atok. So for today's video, I will be having a tutorial video on how to use this Excel program I've made for the design of secondary reinforcement for reinforced concrete beams using NSCP code of 2001 specification and 2010 or 2015 specification. So for me to elaborate on how to use this program, we are going to solve a problem here. And for our situational problem states that the shear reinforcement for the beam shown if it carries a service dead load of 36 kN per meter and a service live load of 54 kilonewton per meter rather, with a FC prime of 28 MPa and Fy of 276 MPa. And here shows the clear span for our beam with a 7.2 meter and a 7.50 meters for C to C length. And here is our cross-sectional diagram of our beam showing the parameters of our main bars and the length of the beam with an effective depth of 562.5 mm and a beam width of 350 mm. So first, here in our program, we are asked for the parameters of our beam. So the problem rather asks or show the value for our dead load of 36 kilonewton per meter and 54 kilonewton per meter in terms of live load. In length of the beam, we are going to consider the clear span value of 7.2. And here, it shows the ultimate uniform load of 142.2 that is being exerted in our beam. So next, we are going to input values given in terms of the dimension of our beam. Remember that the beam width is 350 mm and effective depth of 562.5, which are this one. And in terms of our Fy and Fc, or the steel strength and the compressive strength, it is given as 276 MPa and 28 MPa respectively. So since the value of, in terms of the dimension of our stirrups, the problem didn't give us any value for the diameter of our ties. So we are going to assume value, and it will calculate the value of our spacing, and these values will give us also the value for the shear of our, or the area of our shear, and we are going to test if they are acceptable, or the assumed value for diameter is acceptable or not through these conditions. Also, from the other references I've read, that in terms of the sizes and spacing of main bars and ties, we are going to use 10 millimeters diameter for ties if our main bars is equal to 32 millimeter or lesser than 32 millimeter. And if these conditions didn't meet, we are going to use value of 12 millimeters for our ties, since the value for our main bars clearly lesser than the value of 32, which is the condition. So we are going to use value of 10 millimeters for our stirrups. And for the number of leg, we are going to input the value of 2. Why? Because here in our cross-sectional diagram, it already shows the value, the number of leg here. So after that, it will automatically give us a value of 157.075 for our area of our shear. And here it will calculate values for our minimum required of the area of our shear, and it is clearly be seen that our area assumed is greater than the value of the required. Hence, the assumed value is acceptable. In terms of the verification of the adequacy of our beam, it is required that the value for this condition must be less than the value of our Vs, and it is clearly seen that the value of our Vs is lesser than the value of this condition, so we get a remarks of adequate. So in terms of the maximum spacing of stirrups, the value or the range falls under that our Vs is greater than 2 Vc but lesser than 1/2 Vc. So we are going to use value of d over 2 of 281.25, or the S required of 600 mm, or the S itself of 73 mm. So for our S max, it will give us value of the lesser between these between these three rather, since the value of our S is lesser than the value of 600 and 281.25. Therefore, our S max is 72.896. So below the S max, we got the value for our first stirrup at 18 mm. Excuse me. So for the output values here, at first row, we have a value of S required of 73 and number of bars of 7 and 6. I've highlighted this first row since this is the critical point where the ultimate shear is being experienced, meaning the minimum value for our spacing of the beam must be at critical point, which is this value of 73. And this value of 73 will go further at a number of bars of 13, and at 6 it will be under the spacing of 75, and so on and so forth. I also noticed that as we go further with the value of our X, the lesser the value of our VU. Since the lesser we get the value of our VU, meaning the value for our VS will also be lesser than the previous one. Since the value of our VS is lesser, as we go further with the length of the beam, the spacing also will be greater than before. So if this value of RS is greater than the previous one, so the value of Rn will also be lesser. So it will be economically designed. So I've stopped at 2.5 meters, since as I go further at the value of 3, the value of our spacing required will be consistent. And here at 2 number of bars, it will adopt a value of our spacing of 250. Therefore, the value of the 75 spacing or rest will be in terms of 1. After 2 number of bars at 250 millimeter spacing, the rest will follow a spacing of 275 na. So in continuation for our secondary reinforcement for our design, and so for today's situation, we are going to follow 2010 or 2015 specification. Again, let's input values for our parameters of the problem given. So remember that the value for our dead load and live load is 36 and 54, and 276 of our Fy and Fc prime of 28. And we are going to consider the clear span value of 7.2 for our length of the beam. So we are going to input value of 36 in terms of the dead load and 54 in terms of our live load. The length of the beam is 7.2. We got the value of our ultimate uniform load of 129.6 kN that meter, and in terms of the cross-sectional area of our beam, we got a value of 350 millimeter in terms of our beam width and an effective depth of 562.5. Fy is 276 and compressive strength is 28. And here, it will calculate the value of our VC, the same as the previous one. And since also we don't have the value of our diameter or the area of our stirrups, we are going to assume value of 10. Again, the number of leg of 2. And in 2010 or 2015 specification, it is accepted the assumed values for the diameter of stirrups, and verification of the adequacy of our beam is it is adequate enough. So in terms of our maximum spacing of our stirrup, it falls under the range of 1/2 VC to 2 VC. Under this range, we are going to use the value for our spacing either of these three. Since the value of our S that we solved is lesser than these two, we are going to consider the value of 7.12 as our S max. And again, here shows that our value of stirrup starts at 18 pa rin. So we are going to start our stirrups at 18. So in terms of the output values, here from the table, we got a S required at critical point of 70 spacing under the number of bars of 8 and 6. This number of bars will follow spacing at 70 millimeter, and it will start at 18 millimeter from the face of our clear span of column. And again, notice that as we go further with the value of our X, the value of our VU and VS will also be lesser than the previous one. Since the VS is lesser than the previous one, it is indirectly proportional with the value of S. So it will give us a value of our S will be greater as we go further. And for me to show why I've stopped at 2.5, since at 2.5, the value of our spacing will be consistent at 275 millimeter na lang man. So, for me to show na lang pod, we are going to input value of 3, 3.5, and 4. So, notice that the value of our S required is consistent all through, meaning the number of bars required here will be also consistent at 2. After the value of 4 of number of bars, other stirrups will follow a spacing of 275. And that's all for this tutorial video, and thank you for listening and have a great day.